We have made it. The packet has been DNA'd, it's been transported across the CNI fabric, and it has been successfully delivered by the node's kernel to its final recipient. This is layer 5, the isolated network namespace of the pod.
This is the private office. All the complex infrastructure layers, 1 through 4, have done their job perfectly. Success now rests entirely on the application that's running inside the container. Is the process actually alive? Is it listening on the right address? Is it overwhelmed with work?
And the physical isolation here is really crucial to understand. Every pod gets its own dedicated, isolated network environment.
That's achieved using some really cool Linux networking primitives. The pod gets its own network namespace, which means it has its own local host interface, its own 127.0.1, its own routing table, its own interfaces.
It thinks it's a real machine.
It thinks it's a tiny little virtual machine, and its connectivity to the outside world is provided by a VETH pair. Think of it as a virtual Ethernet cable. One end is plugged into the pod's namespace, and the other end is hooked into the node's main CNI bridge or routing table. The pod's IP is assigned to the interface inside that namespace.
I remember spending, I'm not kidding, 6 hours one night chasing a timeout, only to realize the application was binding to 127.0.0.1. That feels like a frustrating rite of passage for new KES users, and it has to be the #1 layer 5 failure.
It is the most common and the most subtle application error that masquerades as an infrastructure failure. If your application code binds its listening socket only to 127.0.0.1, the loopback address, it's telling the kernel, I will only accept connections that originate from processes inside the same pod.
It's listening, but only to itself.
Only to itself. So when the packet arrives via the CNI addressed to the real pod IP, like 10.244.3.15, the application's binding just ignores it, and the kernel sends back a connection refused error.
So the golden rule for any containerized application is that it must bind to 0.0.0.
0.0.0, which is a special address that tells it to listen on all available network interfaces, ensuring it receives traffic that's routed via the main pod IP.
Okay, beyond that classic binding issue, what other application failures do we see at this layer?
Well, sometimes you see internal container firewall rules that inadvertently block traffic, but more often it's resource related. If the application experiences memory saturation or high CPU load, it might be running, but it simply cannot accept and process new incoming connections fast enough.
It's the TCP listener backlog fills up.
The backlog fills up and the kernel starts dropping connections. To the outside observer, it looks exactly like a network failure, but it is, in fact, a layer 5 performance bottleneck.
When we suspect the application, how do we confirm it's actually listening without having to, disrupt the running container?
We need to peer inside that isolated network namespace, and there's a specific command for that. kubectl exec -podname ssltnp. What is that doing? It runs the SS or socket statistics utility inside the pod. The flags tell it to show all listening, TCP-B sockets, show the numeric ports, N, and show the process that owns the socket. You are looking for a listening TCP socket on your expected port, and you need to confirm that your application process is the one bound to it.
And if I don't see my app there, or if I see it's bound only to 127.0.0.1, that's my definitive layer 5 answer.
That's your smoking gun. The problem is inside the pod.
Finally, we got to circle back to layer 2 here and discuss the critical role of liveness and readiness probes, because they really bridge layers 2 and 5.
This is such a crucial concept. Liveness and readiness probes determine the pod's lifecycle status in Kubernetes. A liveness probe checks if the process is, well, alive. Is it running, or has it crashed or deadlocked? If that probe fails, Kubernetes takes a drastic step. It restarts the container.
It assumes the app is unrecoverable.
Right. But a readiness probe is more subtle. It checks if the process is ready to receive traffic. Is the database connection pool warmed up? Are all the initialization routines complete? Is it not currently overwhelmed?
And if the readiness probe fails?
If the readiness probe fails, the running pod's IP address is immediately and automatically removed from the endpoint slices at layer 2.
Okay.
The process is still running. Layer 5 is technically okay, but Kubernetes marks it as unreachable for new traffic. This prevents Layer 3 from forwarding traffic to an application that is temporarily unable to serve requests. It's a clean way to signal temporary unavailability.
So a readiness probe failure effectively solves that Layer 2 stale endpoint problem we talked about earlier, but it does it gracefully by communicating application state back up the stack.
It connects application health directly to the routing infrastructure. It's the application raising its hand and saying, hey, I'm alive, but please hold my mail for a minute.
That makes so much sense.
So we've successfully traced that single curl request through the ingress, the service directory, the kernel translator, the CNI fabric, and finally into the application. The real mastery of Kubernetes networking, I think, lies not just in knowing those 5 layers, but in understanding how they interact under the banners of observability, security, and performance.